So yesterday we stopped here, and so we said that fan blades are made of titanium skin with a titanium honeycomb inside. So let us take a look and see how fan blades are manufactured. So here we have a
Nestling in the Lancashire Hills, 100 miles north of Derby, Barn Oldswick is where the first ever jet engines were developed by Sir Frank Whittle. And today this small community still plays a very special part in the building of every Trent engine. Raw materials arrive at the factory every day. Solid sheets of high-grade titanium. They're destined to become one of the components that make Rolls-Royce Trent engines truly unique.
When you walk onto a plane, you look into the engine, that's the fan blade, and that's what we make here.
Mike Wallace's job is to transform the raw metal into high-performance fan blades.
The fan blade delivers 75% of the engine's thrust. It shifts about 1.2 tons of air per second, and the loading on the blade is something like 90 tons centrifugal load when it's at full throttle.
That's like hanging 13 double-decker buses off each of the 20 blades. The enormous fan is what distinguishes a modern jumbo engine from older turbojets. They didn't have a fan at the front and relied entirely on the jet exhaust to thrust the plane forwards. Faster than a propeller, but inefficient and very noisy. But in a turbofan, like a Trent engine, the energy of the exhaust is harvested to turn the massive fan blades at the front, which in turn push huge amounts of cold air quietly around the sides of the engine. And that's what thrusts the plane forwards. The Trent fan blades are unique.
So, which section is this?
And it's all down to their design.
The original blades used to be solid, but in order to get better performance, take weight out of the engine, it was designed to be hollow, and our manufacturing processes, which is unique, has actually enabled us to make that and advance the technology within Rolls-Royce.
Every single fan blade is worth as much as an average family car. For each blade, 3 sheets of metal are bonded together to make a solid titanium sandwich. It's a process so secret it can't be shown on television. The unique process begins when the titanium layers are bonded together in a secret pattern. Then the whole blade is inflated like a balloon, pulling and stretching the inner layer across the cavity, like cheese between slices of pizza, leaving a super light, super strong internal structure. But before it can be inflated, the flat titanium sandwich has to be heated and twisted into shape. Then it's ready for the most critical stage of the process, inflation.
We've used an inert gas. We can't have it reacting with the titanium at temperature. It's a high pressure inside to inflate it to the level of accuracy we need.
A heat-resistant tube connects the blade to a high-pressure gas supply. But the gas alone won't be enough to inflate the blade. The whole assembly also has to be loaded into a furnace at a secret, critical temperature. A single speck of dust could cause a lot of damage. And John doesn't get much time to prepare.
It gets very hot. After about 30 seconds you've got to come away. You can't stand there too long at all. If you do, you just start burning. All your gloves, fingers, everything.
It takes 4.5 hours for the gas to slowly inflate the blade to its precise aerofoil shape.
Despite the precision of the engineering,
no two finished blades are exactly alike. And with 20 in each fan, it will only spin smoothly if the blades are perfectly balanced. So every one is precisely measured and weighed, then rung like a bell.
Each blade has a different mass and different frequency, and we use that data to select where those blades are going to be positioned within the disc. So when we go to engine build, they're located and selected in those exact locations.
This is the attention to detail that ensures every Trent engine is as safe and efficient as it can be. And with up to 150 blades leaving the factory every week, it's also the challenge that keeps Mike going.
For me, it's exciting. After 27 years working on fan blade, it's still exciting. There's still a lot more to do.
That we should probably, let me see. So one of the reasons which I did not mention yesterday, one of the reasons why the blade looks highly twisted has to do with these velocity triangles. So as you can see, since the blade speed keeps increasing from root to tip by a large margin, you can also see how the relative velocity vector, although the flight speed, the velocity vector corresponding to flight speed is the same in magnitude and direction, the relative velocity vector keeps moving like this outwards as the blade tip speed increases. So as the relative velocity vector keeps moving, remember, in a frame of reference where the blade is stationary, the relative velocity vector is such that it would be tangential to the blade profile at inlet. And that is why it is the relative velocity. So the blade becomes highly skewed because the angle at which the relative velocity approaches the flow also keeps changing from root to hub. That is why the blade looks so highly twisted, and it has to be. And as was shown in this video, the process of manufacturing this is extraordinarily complex. It is actually inflated to the final position and then machined. So it is extraordinarily complex. Most importantly, what is not mentioned here is that the titanium sheets that they start with is usually melted and re-solidified 3 or 4 times in a vacuum furnace, so that all inclusions, all materials, gas bubbles, nothing will be there, because if any impurity is there, even a tiny speck, that would be the beginning point for a fracture to begin. So it is vacuum melted and solidified 3 or 4 times, vacuum degassed. It is called vacuum degassing. So you remove all the bubbles. That is done 3 or 4 times before they even start manufacturing the fan blade. So that is the sort of purity and quality that you require in these blades, because of the loading that the blades will experience when they are in service. The blades are operating at low temperature. So they are operating at the normal temperature, and there is a pressure rise, but it is not so high. The challenge, as I said, is that the tip spins at very high speeds, but temperature is not an issue here. But crack formation and propagation is due to the centrifugal stress. That is, we will see some of that when we look at accidents and investigations. So we will see that when we look at accidents, some of the accident investigations will highlight that. Now, so as you can see, the designing the fan, both from a thermal perspective and from a design perspective and a manufacturing perspective, as you saw, is extremely challenging. So each fan, a typical high bypass ratio engine would have about 20 fan blades or so, between 20 and 18. Okay. So each fan blade is worth about $50,000 to $60,000 or more in today's dollars, each fan blade. Okay. So that is the kind of technological challenge that they have to go through to manufacture the fan blades. So if you look at the engine as a whole, right, so you have the fan, we have the low pressure system, you have the intermediate pressure system, and you have the high pressure system. Okay, so and these are the operating conditions for this, for the various blades and other things. So looking at this, what would you think as the most difficult component to manufacture? What is the most challenging component to manufacture? We have already seen the fan. There are other things also. So is it the fan or is it any of the other components, and if so, why? to design and manufacture. And when I say design, I do not mean the thermal design part. Thermal design part is relatively straightforward, challenging, but straightforward. When I say design, a selection of materials and then manufacturing, that is what I mean. So, what would be the most challenging component here? Shaft?
Yes, sir, the central shaft.
The central shaft, okay. Anything else? Huh? Blades, turbine, which we have 3 turbines, which one would you think is most challenging? Combustor also sees high temperature. The combustor, remember the combustor has a liner, so the liner experiences the highest temperature. So, right. So, would it be the combustor liner and the high pressure turbine because the temperature is high? But notice that the high pressure turbine, your answer is partially correct. It is a high pressure turbine, but you look at what the high pressure turbine goes through. So, if you look at this green rectangle, this is the region where you see the highest pressure, highest temperature and highest RPM. So, the high pressure turbine experiences the highest pressure, highest temperature and spins at the highest RPM. So, it is even more critical than the fan. So, the high pressure turbine blade you asked me why we have not been able to realize this. It is only because we cannot manufacture high pressure turbine blades, because they are so critical to manufacture and each one is so challenging to design and manufacture, both from a materials perspective as well as a manufacturing perspective, that the technology is very, very critical. Now, each one of this high pressure turbine blade, there would typically be about perhaps 100 to 150 blades on the high pressure system. Each one of those blades costs about $50,000 to $60,000, best estimate, each blade, because it is so challenging to design and manufacture. And again, as you said, it experiences extremely high temperatures. So, let us take a look and see how we go about doing this, okay, the high pressure turbine blades. So, if you look at the blades, if you look at the turbine entry temperature, over the years the turbine entry temperature has been going up like this, whereas the allowable metal temperature has stayed more or less at about 1200 900 degrees Celsius or so, 900,000 degrees Celsius, but the operating temperature continues to increase, because the higher the operating temperature, the higher the efficiency, basic thermodynamics. Right. So, what we need to do is, for the gases, the temperature of the gases that flow over the blade are at such high temperature, but the blade metal itself must be maintained at temperatures which are about 400 degrees Celsius less. So, many things are done. Most importantly, the blades are hollow, as you can see from here. A cut section of the blade shows that the blades are hollow. You can see that here also. So, what is done is, you basically take air, cool air, and then force it to flow. So, this is the blade root. So, there is a passage here. So, you force the air, cool air, to come up like this or to come through like this, and then the air will go up like this. So, it goes through a tortuous passage. So, it goes up, then comes down, then goes up. So, it is a serpentine passage and then comes down, and then you have impingement cooling on the leading edge of the airfoil, because the leading edge of the airfoil, as you will know from your heat transfer, undergraduate heat transfer, that is a stagnation point heat transfer, is where the temperature is the highest. So, the leading edge of the airfoil experiences the highest temperature. So, we use what is called impingement cooling, where the air, cool air, impinges on the inside surface of the leading edge like this, and then goes out like this. So, that is impingement cooling. And then throughout, we make sure that there are rods like this, small rods, which will make the flow turbulent to enhance the heat transfer. And then you also see this sort of pin fins on the surface of the blade. Yeah, so you can see them on the trailing edge. These are on the outside surface of the blade. Small pin fins which are located here to increase the heat transfer area and to promote convection heat transfer. So, this enhances both forms of heat transfer area. It increases the surface to volume ratio, so that the blades can be kept cool. The leading edge and the trailing edge are the most critical components, okay, because the trailing edge is very critical, because there is so little metal in the trailing edge, because it is so thin, there is very little metal in the trailing edge. So, the trailing edge is also a very critical component. So, you force the air then to part of the air to come out of the trailing edge, so that the trailing edges are also kept cool and they do not melt. Okay. So, this is a very critical component. Now, the outside surface, so after the air goes through the inside surface, it comes out and then it forms a film along the surface of the blade. So, the film acts as an insulating barrier between the hot gases which are at a temperature above the melting point and the blade metal itself. So, the blades are always maintained at a temperature below the melting point. So, you have film cooling also on the surface of the airfoil. Okay. So, manufacturing these blades in this sense, from this thermal sense, is very challenging. That is the next question. Where would you take this air from? Where would you draw the air from? That is also a very interesting question. Where would we, I said cool air, right? So, where would you take the air from? From the engine inlet? From the fan duct. Okay. So, you take it from the fan duct because it will be more or less at the ambient temperature, it will be cool there. Yes? No?
But that will have bubbles, because if the air film that is forming is of not same kind, then your local turbulence may create trouble to the.
That would not be an issue. Anyway, we are only using air. The only problem with that idea is that, remember, these passages are extremely small passages. So, if you take the air from the fan stream, it will not flow through this. The pressure drop is very high. So, you would need high pressure air to go through this. Although you would prefer to have the fan air because it is at a lower temperature, it will not flow through. So, basically what you do is you take the air from the high pressure compressor. That is the only one that will go through the passages here. So, you can keep a flow going, and the film also can be maintained, otherwise the film will be disrupted or film may not even form. So, you need high pressure air to go through these small passages. And when I say cool air, that air itself is at a temperature of about 500 degrees Celsius. That is cool compared to 1400 degrees Celsius. That still provides a 900 degrees Celsius temperature difference. You need the high pressure air. So, you draw the air from the high pressure compressor and then use it for blade cooling purposes. The disadvantage to that is that that is air that is not going to participate in thrust generation. So, you have spent power compressing that air and then you are using it for cooling, not for thrust generation, which means its enthalpy cannot be harvested for thrust generation. So, that is a downside. So, the cooling air has to come from here, but you have to live with that. That is the cost, but the advantage is it can be used for maintaining the blades, keeping the temperature also high. Okay. So, that is a price that that we have to pay. So, that is that's okay. And so, this is what is done to keep the blades cool. In addition, because the temperature of the blades keeps increasing, what is done today is, you can also see the cooling passages here very nicely, the internal passages. Today what is done is the blades are all coated with the ceramic coating, which is called the thermal barrier coating or TBC. So, the thermal barrier coating allows the temperature to be increased even more, the operating temperature to be increased even more. So, that is why the the aircraft engines, the peak temperatures that they can go to is about 1600 degrees Celsius or even slightly more than that. So, the cooling plus the TBC. So, you can see the TBC blades, you can see the hollow blades here and also the TBC coating, and you can see the holes for film cooling here. So, this is where the air from inside the blade comes out and forms a film on the surface of the blade to provide film cooling. So, you see the film cooling, you see the fir tree, which is how the blade is mounted on the disc, and you see the blades themselves here. So, this allows the temperature to be increased. So, this will cool this will keep the blade temperature of the blade metal below the melting point. But the challenges still remain. So, basically we said it is exposed to the highest pressure, highest temperature. So, we have taken care of the highest temperature by using cooling and by using the thermal barrier coating. But what about centrifugal loads due to the high RPM? That is still a challenge. Now, how is that a challenge? So, if you look at So, as was mentioned, see, the blades actually experience a lot of creep. Okay. A creep, as you know, is prolonged application of moderate loads at elevated temperatures. Basically, the load by itself is well below the yield load of the metal, but this is prolonged load applied at elevated temperatures, and blades basically stretch. The best example of creep is what happens to the rubber gasket in a pressure cooker. You continue to use it, it is exposed to high temperature. After some time, it becomes, the stiffness is gone. So, basically it has creeped, you have to replace it. Right? Now, fatigue is weakening due to repeated cyclical loading. Now, the cyclical loading comes because of temperature variation. So, the duty cycle of the engine typically is it's idled, then it's at maximum power during takeoff, close to maximum power in climb. Cruise, the power required comes down. Descent also, the power goes up, but not so much, and then reverse thrust, and then again it is idle. Remember, unless the aircraft is in the air, it does not make money. If it is on the ground, you lose money, which means the aircraft repeatedly goes through these kinds of cycles. So, that is what causes the fatigue loading on the blades. Now, the airframe itself undergoes a different type of fatigue. So, if you look at the fuselage, that also is prone to fatigue, but that comes from a different kind of fatigue loading. Where do you think the fatigue loading for the fuselage comes from? So pressurizing, and so when it climbs up, so generally if you look at the cross section of the fuselage of an aircraft, it is slightly oval. Although it is not visible to the naked eye, it is generally slightly oval shaped. It assumes a circular shape only when the cabin is pressurized. So, these repeated pressurizations and then depressurization causes a fatigue load on the skin of the aircraft, the fuselage of the aircraft. Okay. That is that's also a tremendous concern. Okay. So, the engine experiences fatigue for a different reason compared to the fuselage. Okay. Now, corrosion is also a major problem in these blades because of the oxidation of the turbine metal. Usually these are made with very sophisticated alloys, nickel based alloys with chromium and cobalt, but the composition itself is highly classified. Lot of research goes into this part of blade manufacturing. The material science of the manufacturing of HPT blades is extremely tricky and highly classified. Okay. So, these are the challenges. So, we took care of the temperature part through cooling, but still the temperature is high and you can still have these kinds of failures, mechanical failures of the blades. Okay. So, these things have to be taken into, how do we take this into account? So, these things have to be taken into account when we manufacture the blades themselves. Okay. So, we will look at some simple ideas in failure. Okay. So, basically when you manufacture anything, okay, so it has crystals oriented at all possible directions. They have crystals in all possible directions, and in the blades here actually experience centrifugal load. So, if you have a crystal boundary which is normal to the stress direction, so basically a crack starts from there. So, it can be pulled apart like this and a crack is initiated there. The crack then grows. Either it can be an impurity or it can be from something like this. So, the idea to circumvent this difficulty is to have what is called a directional solidification process. So, you basically cast the blade in such a way that all the grains are oriented parallel to the stress axis. So, when the blade is pulled like this and the grains are oriented like this, you do not have the problem of crack propagating like this. It can still happen, but you have reduced the risks tremendously. Of course, the best case scenario is to have a single crystal, no grain boundaries at all for cracks to start from. So, all the modern turbine blades are made of single crystals. Today, the manufacturing process is such that all of them are made with single crystals, and that is what has allowed us to increase the operating temperature and increase the reliability of these blades. Okay. So, these blades have the most critical components in the engine, more so than even the fan blades. They are the most challenging to design, most challenging to manufacture, and they require constant attention. Okay. Inspection of these blades is very difficult to do for looking for small inclusions, cracks and things like that. They have a very detailed protocol for all this. But even then, inspection of these blades while they are in service is very, very difficult to do. and these are the most vulnerable. So, later on we will look at accidents and failures. One of them involves, one of them had to do with failure of a fan disc, other one is failure of a turbine disc. So, we will look at this and then see how these things happen and what has been done to improve these things over the years. Remember, we are looking at accidents and failures. These are not common accidents and failures. As I said in the beginning of the lecture, the in-flight downtime of engines today is one incident per more than 100,000 hours of operation. Okay, so, that is where we are today. So, we have come a long way. So, the videos that we are looking at actually are quite old, but so these will tell us lessons learned and how we have made things better.
Most of the HPTs are ceramic coated.
Yeah, all of them are ceramic coated. All of them, including the engines for narrow body aircraft, all of them are ceramic coated. So, they have all these things, they have internal film cooling and they have TBC and they are all single crystals.
How often do you do NDE to see if everything is alright with the?
The protocol for testing depends on the number of hot hours. So, hot hours is defined as so there is a schedule. So, when the engine takes off, it goes through this duty cycle. The number of hours at which it spends above a certain threshold. For example, exhaust gas temperatures, you look at the margin. And then you also look at the time that the engines are spinning at RPMs above a certain value. So, those are hot hours. As I said, the takeoff and climb are the most critical. So, it depends on how much time the engine spends in these two phases. Those are added up, and so the inspection schedule is tied to the hot hours that the engine operates. And modern engines actually, all of them communicate with satellites, and the data is sent to the manufacturer. So, they have a constant communication. Once every hour, entire engine data is uploaded through satellites to the manufacturer, and they do big data analytics, and things like that, and automatically inform the airlines that this needs to be looked at, in the engine and so on. In fact, interestingly, that was the only way in which the flight path of MH370 could be discerned. Everything else was turned off. But the communication of the engine with the satellite is not in the pilot's control, that takes place automatically. So, that was done through Inmarsat, and by backtracking the Inmarsat data, the flight path of MH370 was worked out using that. So, this data is continuously monitored. So, there is a set schedule for that. The engine has to come on wing inspection and then off wing inspection is all done, but nowadays the monitoring is continuous, but the NDE monitoring is not continuous. If there are problems, they are usually detected and the engine is taken down for inspection, but NDE inspections they have fixed schedules for that. So, every time an accident happens and it is traced to, let us say, fan disc failure due to crack or turbine disc failure, they do root cause analysis and then change the protocol to modify the inspection procedures. So, let us see how they manufacture high pressure turbine blades.
Come to an end too soon.
At the heart of every engine is a ring of 96 turbine blades that are the most amazing components in the whole engine. Jet engines work by sucking air into the core and through multiple compressors. Squashed to a 50th of its volume, this air is forced into a combustion chamber, where it explodes with fuel to create a ferocious gas jet. This jet is met head-on by the turbine blades, spinning them so fast that each blade delivers the same horsepower as a Formula One engine. The job these tiny blades have to do is unbelievably demanding.
The blade exists in a fairly harsh environment. It has to rotate at about 10,000 revolutions per minute, the blade speed of about 800 miles per hour. The component itself operates at something like 300 degrees above the melting point of the alloy.
To operate at around 1700 degrees, they're designed not to melt.
Here you see the gas streams moving around the airfoil. At the bottom of the blade is the fir tree area, which is used to hold the blade into the disc. Above it you see the aerofoils with a peppering of cooling holes.
To stop the blade melting, Rolls-Royce designers used computer modelling to design a blade that has a precise pattern of tiny air passages throughout.
Here we see what the blade would look like if we didn't have it cooled. And you can see that there are some areas of red, which means that the component is too hot. We put a cooling system inside of the blade, which cools it down to safe levels, and that cooling system takes away the same amount of energy that would boil a kettle in a 20th of a second.
But even with the cooling holes, no ordinary metal would be good enough. That's where the company's materials research, no ordinary metal would be good enough.
So let me just stop here for a second. I wanted to show something that we will come back to later on. So as you can see, the turbine blades, there are two ways of mounting the turbine blades. So here as you can see, the turbine blades, the fir tree region is parallel to the axis. So you have these slots and they are fitted parallel to the axis. That is one way of mounting. The other way of mounting is to have a circumferential slot, and then the blades would be mounted like this. So either the root of the blade either is circumferential like this or along the axis like this. Here you see the axial mounting. This part is called the disc. So this is the part that is eventually connected to the shaft. The blades themselves are not connected to the shaft. The blades are mounted on the disc, and the disc itself is connected to the shaft. Okay, so we will come back to talk about the disc later on. The disc experiences a lot of centrifugal stress, so it is a very, very critical component. So we will discuss that as we go along.
With the cooling holes, no ordinary metal would be good enough. That's where the company's materials research laboratory comes in, creating new metals with exactly the physical and chemical qualities demanded by the designers.
To try and achieve the properties that the designers want, we will design some trial compositions of alloys with different recipes, different blends of the alloy constituents, and then we will test those samples on different mechanical and environmental tests, and from that we'll choose the best possible blends which will deliver exactly the balance of properties that they require.
Using electron microscopes, the materials scientists can precisely analyse the microstructure of the alloy, checking that the crystal structure and mixture of metals is exactly as intended.
We've got a team of research specialists, about 25 in the team here in the UK, and there are teams in Germany and the States as well. And we're trying to draw on all the expertise that exists in the academic network around the world to bring all the best expertise we can into Rolls-Royce.
Even the finely balanced alloy recipe isn't the most advanced technology in the turbine blade. To cast the metal into its complex shape, a unique process is used, and it's another very closely guarded secret. It's done at a purpose-built foundry in Derby, where one of the few people who knows the secret is casting engineer Owen Draper.
If you take a normal piece of metal and solidify it from being molten, you'd end up with something that looks a bit like a granite worktop. Lots and lots of little different crystals, all in different directions. That's not very strong because the different crystals, the joins and the boundaries between them, they just cause a weakness. So what we aim to do here is to create a single crystal. Single crystal, no crystal boundaries, therefore it's an awful lot stronger.
The blade is made by growing a single crystal of metal into the correct shape. It's incredibly complex and demands a huge team of people working round the clock. But it starts with an intricate, hand-built model of the blade in skilled hands like Maureen Hankey's.
I've been doing it on and off since '73. Skill is you've got to be very dexterous, everything's got to be perfect, everything's got to be smooth.
The secret part is the way the molten metal is cooled through a spiral tube at the base of the mould. The tube prevents all but one crystal of solid metal from passing through, allowing that single crystal to grow throughout the mould. Imperfections could ruin the casting at any stage. Even the wax models are x-rayed by keen-eyed inspectors like Jackie Brown.
We were looking for defects in the core, i.e. cracks, chips, voids. When it's sentenced to scrap, is broken in half and put into the bin.
Once cast, every single blade is thoroughly checked and checked again by eye, by computer, and by X-ray. Even then, they're far from ready. Each blade goes through another 4 days of precision finishing in the hands of machinists like Steve Ball.
We're all very good at what we make. We don't sometimes share it. It's not until you see Trent Fleet fly over, I've made my own good bit of that.
And because of the extraordinary demands on the blade, its dimensions must be accurate to within 1/10 of a hair's width.
We grind the fir tree to within 7 microns, which is a hell of a tight limit. Goes under a load of 18 tons, that does. If we stretched it with 18 tons, re-gauged it, there would be nothing. Everything would be to the micron the same. There's no alterations in the structure. There's no cracking. There's no stretching of anything on there. And bearing in mind, you've got 96 of those in an engine set. Every one is like the first one. It's perfect. It's like a brand new baby. You treat it like that. That's why the focus of everybody in the shop's the same, whether it's 6 in the morning, 6 at night, 12 at night. Everybody's the same. The next one's always the most important because all the rest are good. Because we've never had one come back. You can't argue with that.
It's the skills of people like Steve and the cutting-edge technology that keeps Trent engines ahead of the game. But innovation is a risky business. Designing the Trent engine almost brought Rolls-Royce to its knees.
So you can see now why the HPT blades are the most critical components, most expensive component in the engine. You know, this kind of technology is something that we are yet to develop, both on the material side front, manufacturing front and machining. So I think we still are a long way off. We will see. Any questions? All right.
Come to an end too soon.
Now, one of the probably one of the most they will have their own combinations. Yeah, they are all totally, completely classified. So and patented also. Yeah, basically, I mean, nothing stops you from or any of these companies from buying their competitors' engines, tearing them apart, and then looking at them, which I'm sure they do routinely. So yeah, so it is only what improvements you make, but you cannot reverse engineer it. That would be that would put you in a lot of exactly. Yeah, so so you sort of look at it and then see how to go forward and so on. Okay? Yeah. Well, the question is, if you lowered the bar, what kind of engine are you trying to manufacture? Then you have to lower everything else. Then the thrust that you develop also would have to go down commensurately. So basically, you are now gone from trying to manufacture a high bypass ratio turbofan to possibly a low bypass ratio turbofan engine. So what is your mission? So if it's a low bypass turbofan engine, yeah, perhaps we can do something like that. Yeah, a lot of things have to go go right, priorities, many things have to go right for that to happen.
We will always be in the catching business because these two big players are going to improve.
Everybody is in the catching business, unless you are from China, where you can just copy and reverse engineer and then get away with it. Everybody is in the catch up business, you know. So, yeah, I mean, you know, these companies have too much of a head start, and so catching up will be difficult. But one thing that probably may be working in our favor, I am not so sure, but working in our favor is that the technology appears to be maturing. We seem to be sort of, you know, hitting a ceiling in terms of where we have taken these engines. So perhaps, you know, with time, you know, now we are saying if you buy the engines, we want technology transfer. So perhaps with all those things, you know, we may actually be able to finally start manufacturing these things on our own. That is the only way actually. So yeah, I mean that but there are many other things in the engine which are extremely challenging. You know, if you want to use it for commercial aviation, the demands are incredibly high. You know, we have looked at some of the aspects. In fact, the next one that we look at is even more interesting. That we talked about you know, so many turbo machines, right? You talked about compressors, you talked about turbines, right? One thing that we probably did not mention was we assumed that the air would go through the blades, because only when the air goes through the blades the turbo machines work effectively. Now, what about the clearance between the tip of the blade and the casing? How high should that be, or how small should that be for this turbo machine to work effectively? Because if the air, if you do not do it properly, especially on the turbine side, the air would simply go around the blade. It will not go through the blade, it will simply go around the blade, which means that, you know, it is not going to, it is not generating power, because it will, the enthalpy can be harvested into power to run the compressor only if the fluid goes through the turbine blade passage, not around it. So if it goes around it, then that means, you know, we have to burn more fuel to achieve the same level of thrust, you know, which means it is fuel inefficient. It also degrades the life of the engine. If you burn more fuel, the peak temperatures go up, so your margins come down, you know, so it reduces the life of the engine. So eventually it turns out that, you know, the gap between the tip of the blades and the casing is perhaps one of the most important things that you have to think about. Now, why is that so difficult to do? As the engine goes through its operations, you know, idle, takeoff, maximum power, maximum temperature, cruise and so on. Of course, these are all made of metals, you know, they all expand. So you have some clearance to begin with, you have perhaps no clearance, you know, when because it is exposed to such high temperatures, you know, so and centrifugal loads, you are going to have a lot of difficulty, you know, when as the plane goes through these cycles, as the engine goes through these cycles. So how do you maintain the tip clearance? It is going through these cycles regularly, you know. I mentioned that, you know, I went to Portland, you know, in that aircraft. That aircraft, you know, runs between Chicago and Portland almost 4 times a day. What would be the worst case? Good point. What would be the worst case? Max power. So max power. So the engine is in a max power setting when it is taking off. So if you design for that, when you are operating at idle or cruise, for example, we have bigger gap. Remember, in the duty cycle of the engine, where does the engine spend the maximum time? Cruising mode. That is when you do not want to have a large gap. So what is the worst case design? It is an extremely challenging problem. But how do you do that actively, right? You know, because the change is so much, you know. At idle, if you look at the idle RPM of the high pressure turbine, that would be about 50 to typically 60% of the rated RPM, right? So, and then when it is taking off, depending on ambient temperature, it can go up to perhaps 110% rated RPM. Doing takeoff and climb, you know, and then it comes back down, you know. So how do you, you know, make sure that the case and the blade goes through this? I mean, how do you maintain the clearance? And you want extremely tight clearances. To give you an idea, the clearances typically would be about 0.03 inches. You have to take that into account, I mean, you have to design it so that it is, it can be maintained, and that is a very, very tight clearance, 0.03 inches. That is about 2 millimeters or so. So, maintaining that kind of clearance in an engine that is working like this, and that too we have to do it actively all the time as the engine goes through these things, right. So, what do we do? Who do we turn to? I mean, we cannot ask the design people to design anything differently, right. They have manufacturing people, what would they do? They have manufactured the blade perfectly, right. What would they do? So, what does that leave us with? You can't ask the design folks, right. You can't ask the manufacturing folks. So, who are left? You have to come back to the thermal folks, and they have come up with a very creative solution for this. Let us see what it is. So, this is a trace of engine clearance. Not only is the cycle challenging, but during operation, the engine, as you can see from here, the FAA mandate is that the engine should go from idle power to full power in about 5 to 10 seconds. From idle power to full power in about 10 seconds. So, as you can see, the engine starts with some amount of clearance, and the clearance decreases to this value, and then so that is the takeoff power. So, the clearance sort of then comes back a little bit, then it is maintained here, and then the clearance increases as you go up to to again idle power, ground idle, and then again when it is accelerated, the clearance decreases. So, this is a typical clearance speed, and the speed is also given here. So, the RPM goes up, as I said, it should go from idle to max power in about 5 to 10 seconds is the mandate, is the FAA mandate. So, trying to maintain the clearance under these kinds of conditions is extremely challenging to do. So, basically what thermal engineers people do is, you just take the cold air from the compressor and then spray it on the case. You control the amount of air you spray, so that you can shrink and expand the case as required. That is how you maintain the clearance from the compressor. You can take it from the fan stream, because this does not require high pressure, you are just spraying it on the case, right. You can take it from the fan also. So, you just take air from the fan or compressor, low pressure compressor, then spray it on the casing. So, by adjusting the flow rate, you can have custom designed expansion or shrinkage of the casing as the engine goes through its thing. This is active tip clearance control for the high pressure turbine blades. So, what this will do is, this will improve your specific fuel consumption, because you are maintaining such a tight clearance. So, it improves your fuel consumption, it improves your exhaust gas temperature margin, because you do not have to burn more fuel and run the engine hotter. You can try to run the engine at the minimum possible maximum temperature, and it also increases the time on wing, because if you burn more fuel and your exhaust gas margin comes down, then the engine has to come off of the wing for more periodic inspections, because it is running hot. The hotter hours will increase if your exhaust gas margin comes down. If your EGT margin comes down, the number of hours increase. So, it has to come down for frequent inspections, and the life of the engine degrades. The life of the engine is pretty much determined by the time, the hot hours of operation. So, airline companies will do anything to make sure that the number of hot hours are as small as possible or as minimal as possible during each takeoff and landing. There are many things, there are things that the pilots can do depending upon the load on the engine, depending on the takeoff weight and things like that. That is why takeoff weight is a very, very important quantity that is handed to the pilot just before the flight departs. So, accurate takeoff weight is very important, because based on the takeoff weight, there is a maximum permissible takeoff weight, and if the takeoff weight is less than this, then during takeoff you need not take the engine all the way to full power. You can use more of the runway and take off with less power. So, the takeoff roll is longer, but you are taking off with less engine power, which means the hot hours are brought down, which means the engine life is extended. So there are a lot of things that that pilots can do, which they routinely do to take advantage of these kinds of situations. But of course, you cannot say that you will use the entire runway for takeoff, because sufficient margins have to be given for rejected takeoff or aborted takeoff. So your takeoff roll cannot be beyond a certain margin, the threshold. So there is a landing threshold, there is a takeoff threshold, you have to abide by all those things, but within that there is a considerable freedom depending on the takeoff weight and things like that.
This takeoff process is not yet automated.
It is fully automated.
So what is the pilot going to do?
No, what the pilot does is, see, once the takeoff weight is known, so you then enter it into the computer. You look at the speed, the VR for the rotation speed for taking off, the distance required and all that. Then you adjust the setting in the flight computer. It's called a flex temperature. So you adjust the temperature so that the engine, when you set it at a particular setting, it will produce less than the maximum thrust that it can produce during takeoff. So those are things that the pilot will do. You need to feed the data, double check, do all those things, because if you don't do it carefully, there was an accident, if I recall, Air India Express in Trichy airport, where it took much longer. I think some data was incorrectly entered, so it barely cleared the boundary wall. It brought down the ILS equipment at the end of the runway, and it just barely cleared the boundary wall. But there was another incident when another Air India Express, I think the landing gear was damaged, but the pilot was not aware of it. They continued to fly, and in fact eventually, if I remember, they were informed and they had to divert. The nearest airport that they could divert to was the destination itself. They did not want to come back to Mumbai, they diverted to the destination airport. So yeah, so you have to do all these things extremely carefully. The data is checked and double checked, and so on. So there is a very standard protocol for all these things. Yeah, but eventually the work is all done, in the flight computer. Yeah. It depends on how well it has been maintained. Most of these engines can run for a long period of time. Depends on the quality of the spares that you get. One of the biggest dangers in the aircraft engine market today are spurious engine spare parts. Even airline companies now, there is a big scandal going around the world. It's the market is in billions of dollars. Even major aircraft companies, engine companies, are discovering that, or airlines are discovering that they have spurious parts in their engine. So that is a major that's a major problem. It will run for decades. Yeah, it will run for decades. With the regular maintenance, there is a standard protocol for all these things. So if the airline companies adhere to all these things, then it will run, for a couple of decades at least. The fan blades are composite now. The 9X has composite fan blades. It's not made of titanium, it's made of composites, carbon fiber. They are also long life. Yeah, they are lighter, they are also long life, but composite brings with it different set of problems. In metal we talked about cracks, and other things. Composites has its own special problems, unique to composites. Okay, so let us take a look at how these engines are tested. We will go through a few of these videos. They should be interesting, hopefully. So
recently, Boeing completed the first flight of the GE90-115B powered 777-300ER aircraft. The GE90-115B engine was developed by GE Aircraft Engines exclusively for the 777-300ER. The GE90-115B engine delivers 115,000 pounds of takeoff thrust to the 300ER and represents the highest thrust jet engine in aviation history. Key certification testing was conducted at GE Aircraft Engine's outdoor test facility located near Peebles, Ohio.
IMSO 837, begin icing cloud.
Burst to takeoff. 953.34 on point. Continue hailstorm for 30 seconds.
We'll turn on water flow of 1100 GPM. Water on. IMSO 637.48, burst to takeoff.
So even under heavy rain, the engines can operate without any problem. So the rainwater is simply diverted around the compressor blades and sent out through the outlet. So the combustor will still operate, the engine, the combustor, it will not flame out due to a heavy rain. So they are designed to fly at extremely heavy rain. The only problem is whether you can land in heavy rain. So landing in heavy rain is a different story. The engines will not flame out. We will not have an in-flight shutdown due to heavy rain. They are tested for very heavy rain. So you can see the huge cloud behind the engine. So this is a bird ingestion test.
Seven, call back to runway 30, wind column, clear for takeoff.
Godspeed.
So you can see the engine that is being tested. It looks completely different from the other engines, as you can see.
Welcome back, gentlemen.
Nice to be back.
Time is 23:57. We start transit 51:46. Accelerator triple red line.
So this is what is called the triple red line test, when you max out the pressure, the temperature and the RPM. So you red line all these things. So it's called the triple red line operation to see whether the engine is able to withstand that.
Time is 0001, on point, triple red line. Take ADS 187, engine log 211. Fan 2617, core 11,321, EGT 2013.
So you can see N1 is maxed out, N2 is maxed out. EGT is also maximum.
Boeing and GE aircraft engines, developing products that reduce the size of the world with safety, comfort, and reliability.
This is the containment test. So if the fan blade happens to come off, will it be contained within the engine? So the fan blade comes off. So the engine is destroyed. We will see that again in greater detail later on. So basically what happens is, as you have the fan, there is a band of Kevlar which is kept around the fan blades. So when the fan blade comes off, it should be contained within the casing. It is designed for most cases, but you will also see one accident case where the fan blade did come out of the engine.
The engine became the jewel in Rolls-Royce's crown. And it still is today as the basic design of the entire family of Trent jumbo jet engines. Launching Rolls-Royce onto the international stage, the engine helped them grow from a small player to a global competitor. Today, Trent engines are fitted to half the world's big passenger jets, with new orders worth over £40 billion. At the heart of the Derby factory is the main assembly line for all Trent engines. The line has to run like clockwork to take every build from first components to completed engine bang on schedule.
From the moment we launched the kit to make the first internal module right through to the engine being dispatched, it's 20 days.
The countdown starts with assembly of the biggest and most complex modules. Hundreds of precision-tooled blades, hand-fitted and finished to perfection. 4 days in, and work begins on the engine's Kevlar-wrapped aluminium fan case. Over 4,000 engine control and transmission parts, fitted and wired, every one by hand. At the same time, an army of expert fitters begin the 9-day task of fitting together the engine's 8 separate modules. The first 5 sections are stacked one on top of the other. With gravity helping the process, it's a lot easier to achieve a perfect fit. Every bolt is adjusted to a precise torque, and there are moments that require absolute concentration.
Going down. So you can see the shafts, concentric shafts in this instant. You can see the spline joints,
the whole of the 04 module before we arrive at the coupling in the 03 module, and we take all the care we can not to touch the sides. If it ticks the paint off the shaft, then we have to recoat the paint for protection. It's the trickier of them all to fit, mainly because of the coupling that you can't see and the adjustment that's needed. Going down.
And there's the 2 shear keys that will ride up and locate in the slot. You should hear as it clicks. They'd have clicked in now.
1 week into the build, the fan is assembled from its kit of blades. And with each one worth as much as a family car, it takes an expert touch.
We prefer to wear gloves. It keeps fingerprints off the blades and this grip as well. So it does stop them slipping out of your fingers.
You don't want to drop it, do you?
Certainly not. Certainly not.
So basically, as was mentioned earlier, each fan blade is slightly different in terms of characteristics. You saw earlier that they sort of strike a hammer and ring the fan blade. I think Abhijit Sarkar will be able to tell us how you should stack them together. So, as you can see here, the blades are assembled diametrically opposite. You place one blade and the diametrically opposite blade is placed on that side, so it is perfectly balanced. So, they are all, and that information is drawn from the ringing test.
Before the fan can be fitted, the towering engine stack is craned onto its side. Two tons of precious metal swinging just feet from the ground. Finally, in the position it'll spend the rest of its life, the engine's ready for the last two and biggest modules.
So, you can see the fan casing there, the one light brown. That is the Kevlar fan casing.
The fan is a perfect fit. Its tips clear the lining of the case by a fraction of a millimeter. Yet in flight, will spin faster than the speed of sound.
You don't have the tip clearance problem with the fan
After
because
2 weeks of
it does not
assembly,
go through a thermal
every
load.
completed engine is fitted with vast aerodynamic ducts and inched across to the factory's purpose-built flight test centre. Here, it'll be fired up and put through its paces in a simulation of the harshest flight conditions.
3, 2, 1.
While engineers monitor vibration, rotation speeds and temperatures to ensure everything performs perfectly.
Vibration's looking good. Max conditions now, hands down.
So, this is also a triple red line operation.
1,
Signing off newly built engines isn't all they do at the test centre. Dave Benbow is in charge of testing prototypes for new engine designs before they ever take to the sky. And that means carrying out tests that are much more challenging.
We run thousands of hours of testing. Our primary requirement is to show that the engine is safe to fly, that it's airworthy. We conduct a number of tests to do that, but really we're trying to meet the regulations of the safety agencies. This engine is a flight test engine, and in that extent it has a lot of instrumentation that production engines wouldn't have. That you can see here is led up off the engine and into the pylon so that we can record the data on the test bed when it's installed.
Testing is so exhaustive, it can take 2 years for each new design.
The cold start test is a very important test. We need to be able to start the engine under cold conditions, cold as minus 40 degrees.
Removed from its giant freezer, everything must...
So, the engine is kept overnight in a giant freezer at minus 40 degrees Celsius, and then you try to see whether the engine will start.
Still work perfectly when the engine is started.
We have to make sure that the gearbox will turn when we start the engine. Other tests, so water ingestion.
Water is poured in at 30,000 gallons an hour, but there must be no loss of thrust.
We have to demonstrate that the engine can cope with rain and hail ingestion, and that the compressors can cope with the amount of water going through the engine that it might get in flight, and that the compressors continue to run and that the combustion system remains stable. But one of the key safety requirements we have to ensure we meet is that in the unlikely event of the release of a fan blade, that it's contained by the fan case. Well, it's an absolutely key test in that we need to make sure that there's no chance of the fan blade escaping. On the test, there's an explosive detonation which releases the blade from the disc at max takeoff speed and fires it into the fan case. When this event happens, the energy that's generated by the blade coming off is about the equivalent of a 1-ton car being dropped off a 200-foot cliff. And the casing here then has to retain that and ensure that nothing is released outside of the fan case structure. So it's a hugely expensive test. But our commitment to safety and demonstrating requires us to take that asset and to complete that test, irrespective of what we're left with in the end.
the engine is destroyed. Although it's contained the blade and run down safely, the components that are in that engine will not be used again. Effectively, that engine is then written off.
Only by sacrificing an entire engine like this can they be sure the fan case really does its job. It's 6 in...
Now this is very interesting. Metrology.
Once every engine is built and tested, its last stop is the customer delivery centre, where it has to pass scrutiny by engine inspector Mike Riley. It's a huge responsibility. His will be the last eyes to see inside the engine before it takes to the sky.
I've been at Rolls-Royce for 5 years now. In fact, this month. Before that, I was in the military as a helicopter technician on the first line maintenance. I've actually wanted to work for Rolls-Royce for some time before I came to work here, and it took me 2 years of applying before I could get in. So it's not the easiest place to get into.
Mike's is one of the most specialised jobs on the assembly line. Like a doctor doing keyhole surgery, he uses a borescope to inspect the inside of the engine.
Basically, every single rotating stage within the engine we'll look at, plus the combustion chamber. Literally, the whole of the inside of the engine is borescoped. This is the first stage HP compressor. At the moment, I'm turning it rearwards. Usually the blades will come towards you. I'm just looking for any damage on the actual blade surface, leading or trailing edges. Occasionally you can get a little bit confused in there because there are so many blades. This is the first nozzle assembly.
So you can see the cooling holes on this
assembly that we're looking at, with all the hundreds of cooling holes on it. It's possibly the hottest part of the engine here. You know, practically a surgeon.
After Mike's final inspection, another...
So let us...
There's a big day ahead.
Close this with the last video. So we now go back to the Boeing airfield where the engine,
Today,
first engine is
all
being
eyes are on
tested.
the performance of the Boeing Dreamliner, and of course, the Rolls-Royce engines that power it.
So we started with this, now we will finish with this.
It's a big day for the aeroplane out in Seattle, and an even bigger day for the team of engineers back in Derby, watching the preparations for the flight live online. As the aircraft prepares to take off and the engines fire up to full power, there's nothing anyone can do but wait, watch, and see what happens next.
And here she comes, the 787 Dreamliner.
Way to go, Rolls-Royce!
It's a massive coup to provide the engines for a new airliner's first flight. And it's something to be very proud of for the people who build them.
Quite an emotional moment for everybody involved, particularly for all the guys here who have built the engines, all the engineers who have designed it over the last 4, 5, 6 years. Some of these people have devoted their entire lifetime at work to this.
Ecstatic, really delighted to see the aircraft take off after what's been a pretty long and tiring journey to get this far, really.
But the success of the flight can only really be gauged when orders for the new engine start coming in.
Great news, another order for 5 Trent 1000 powered Boeing 787 aircraft placed this morning. Particularly good because it's quite a tough market at the moment, and so it does show testament to the technology in this engine that even in this market people are still placing orders. it's a great day to be in the job. It's a great day to be in Rolls-Royce. It's a great day for Derby.
For the 11,000 employees in Derby, it's another ordinary day, with more Trent engines to build. And in Warwickshire...
Narasimhan, you had a question yesterday, how they start these engines? Okay, so you don't start the fan, because the fan typically requires about 30,000 horsepower, so you don't start the fan. So what you do is you start the, you can't use batteries also. So what is done is when you start from what is called a cold and dark, that means the plane has been sitting, for a while. So you have the battery. You start the small gas turbine engine at the tail of the plane. It's called an auxiliary power unit, or APU. So you start that, and then you take, once it is running, that can be started with the battery. So you take the air, the bleed air from the compressor in the gas turbine engine, and then send it to an air turbine, which is part of the starter unit. So the air turbine, the shaft of the air turbine is connected to the high pressure compressor. So you turn the high pressure compressor, and once the high pressure compressor starts turning, you can also use a compressor card from ground, that is also possible. But so the compressor card will supply air to the air turbine. So the air turbine is connected to the HP shaft. So it starts spinning. Once it reaches something like 15% of its rated speed, you turn on the igniter in the combustion chamber, and once it spins up to about 25% of its rated speed, you turn on the fuel. So then combustion takes place, and the engine should start spinning up on its own. So once it reaches about 55% of rated RPM, which is its ideal RPM, the starter is disconnected. So by this time, as the HP rotor starts spinning and the fuel is flowing, slowly the N1 shaft will also, so the high pressure shaft is typically labeled N2 shaft. So as the N2 comes up to idling speed, the N1 will also start spinning and reach its idling speed, which is typically 25% of its max speed. Okay, so fortunately I have prepared, I have a couple of videos, not prepared, I have downloaded a couple of videos, we can take a look at them. The trailing edge of the we will come to that towards the end. Yeah. So I think I have. So let us look at. I have a couple of videos. Both are very good. Let us just go through them. This one gives slightly more details. So let me see.
The GE90 is the world's most powerful commercial jet engine in service. The Boeing 777, the best-selling wide-body aircraft of all time. The combination of the engine and the airframe is nothing short of an engineering marvel. In this comprehensive 777 engine series, we will build up the engine from scratch and understand how all the components function as we start and operate it. The engine has two rotor shafts, high pressure shaft and the low pressure shaft. A stator and a rotor combine to form a single stage. The N2 shaft has 9 such stages of high pressure compressors and 2 stages of high pressure turbine. The N1 shaft has 6 stages of low pressure turbine, 4 stages of low pressure compressors, and ahead of them is the massive fan. Before we look at more engine components, let's do the aircraft configuration for engine start. First, the battery switch. Battery provides limited power, good enough to start the APU, a small engine in the empennage of the aircraft. Rotate the APU start switch, hold for a second and release. The APU is online. Now we can use the APU generator.
So the APU is
Selecting
located in the tail of the
switch
airplane.
Establishes full electrical power of the aircraft. During engine start, electrical panels will provide power to the electronic engine control, installed on the engine fan case. APU will also provide the pneumatic power to start the engine. Make sure the bleed switch is in auto position.
So we bleed high pressure air from the APU to start the
Next, the fuel panel selections. We only require fuel from the left main tank, so select the 2 left tank pump switches. 2 boost pumps inside the fuel tank. Transfer fuel to the engine spar valve in the wing aft spar section. Aircraft configuration is complete. Let's attempt an engine start. On the engine, the pneumatic pressure reaches the start valve. 777 has an auto start feature. When used, the EEC takes over the entire engine start operation. Now turn the engine start switch to start position. EEC gets the start signal and power to operate. EEC commands the start valve to open. The pneumatic pressure reaches the air starter. The air starter drives the accessories gearbox. Several torque-requiring components are mounted on the gearbox. One of them is the horizontal drive shaft that connects to the transfer gearbox. The transfer gearbox changes the axis of rotation and with the help of a radial drive shaft, rotates the N2 shaft. As N2 rises, airflow is established through the core of the engine. Due to the airflow, N1 shaft has positive rotation. Fan rotation in turn leads to bypass airflow through the engine.
So you can
At
see on the
7%
bottom,
N2, a small alternator installed on the gearbox supplies power to the EEC, and the airplane power supply goes into standby mode.
so you can see the engine N2 RPM coming up
Since
here.
we are doing an auto
as it is
start, we
rotated.
can use the fuel control switch and need not wait for the engine to reach 21% N2, which is the case in manual start. Let's select the fuel control switch to run and see how the fuel travels within the engine. The fuel control switch opens the spar valve, and the fuel rushes to the main fuel pump. The pump driven by the gearbox increases the fuel pressure and transfers it to the fuel oil heat exchanger, where fuel picks up heat and cools down the engine oil. From the heat exchanger, fuel travels to the fuel filter.
So this fuel oil heat exchanger is very critical, as I mentioned in my first lecture, for transpolar flights because of the danger of fuel freeze. So this is where the fuel gets takes heat from the oil, engine oil, which is used for lubrication between the shafts and so on. So that is very hot, so that is cooled down, and the fuel, which is cool because it is coming from the wing tank, is heated up so that there is no danger of fuel freeze. So this heat exchanger is a very, very important component for the transpolar operations.
Filter screens the fuel for debris and transfers it back to the pump.
Go ahead. Which one? That is the engine test starting from cold. So that is just starting from cold. The fuel would not freeze there. That should be okay. Yeah. The transpolar flight is for extended periods of time over cold air masses. That is why there is a danger of fuel freeze from the wing tanks.
From here, the fuel is sent to the hydromechanical unit. The HMU now controls the fuel to the engine for combustion, and any excess fuel is bypassed back to the pump. HMU waits for the EEC command to open the fuel shutoff valve, and EEC waits for N2 to reach 21%.
About 21 to 25% is when the fuel flow is started.
As N2 reaches 21% RPM, EEC sets up the engine for combustion. Out of 2 ignition exciters, EEC commands one to activate, keeping the other as backup.
So these are the spark
The
plugs.
ignition exciter converts the input power to high voltage pulse and transfers it to the igniter plug. 3 seconds after ignition activation, EEC commands the HMU to open the fuel shutoff valve. Before heading to the combustion chamber, fuel travels through the fuel flow transmitter and back into the HMU. Fuel flow transmitters send signal to the EEC to determine engine fuel consumption, which is crucial for engine performance monitoring. Fuel is now sent for combustion through 2 manifolds, to which are connected 30 fuel nozzles.
So you can see the annular combustion chamber here.
Each fuel nozzle has 2 sprayer tips, and each tip goes into the swirler slots in the combustion chamber. The swirlers diffuse the core airflow, slowing them down, ensuring proper fuel-air mixture, and buying enough time for efficient combustion. Combustion gas forces directly affect the turbines.
So you can see the N2
Since they are
RPM
mounted on
coming
the
up
same
now.
shaft, increase in high pressure turbine rotation drives the high pressure compressor at a faster rate. Likewise, increase in low pressure turbine rotation drives the low pressure compressor and the fan.
So N1 also comes up.
As a result, the rate of airflow through the engine increases, leading to steady increase in thrust. Temperatures inside the combustion chamber is adequate for sustained combustion, therefore at 56% N2, the EEC deactivates the ignition system. At about 64% N2, the EEC commands the start valve to close, and the pneumatic pressure to the starter is cut out, disengaging the air starter from the gearbox rotation. As the engine reaches and stabilizes at the idle power, EEC sends a signal to the airplane systems that the engine start procedure is now complete. This allows the airplane systems to de-energize the start switch latching solenoid so that it could return to normal position, ready for next start attempt when required.
So you can see that the idling RPM of the N2 shaft, idling RPM itself is 70% of max RPM. Whereas for the fan, the idling RPM is about 20 to 25% of max RPM. So once one engine is started, we need not use the APU to start the other engine. The bleed air from here can be used for starting the other engine. So that is how it is started. That is the thrust reverser. No, that is the thrust reverser. It completely reverses the direction of the airflow. Yeah, there are different forms of thrust reversers. That is used in the old type of engine, that is called a clamshell thrust reverser. So you get 2 buckets which come out like this, and the buckets then divert. That is used in the old engines, where the turbojet engines, where the thrust was developed entirely from the core. Here 75 to 80% of the thrust is generated in the fan, which means you cannot use that. Let me see if I can, I think it was there somewhere, let me just see. So here you can see the thrust reverser. This is one form of thrust reverser. So this is actually in the fan stream, so it deflects the fan stream to the front. So that because the fan is producing the majority of the thrust, you have to do thrust reversing with the fan stream. So this is one design of thrust reverser. Okay, so but the same Rolls Royce also uses a slightly different form of thrust reverser. Let me see. So now you can see a slightly different form of thrust reverser. So basically this has vanes inside which deflect the air like this. So there you saw 4. In this design, it has a set of vanes which deflect the air backwards. So that is in the fan stream. That is why the other one is what is used for turbojet engines. Which one? Fuel tanks are in the belly of the aircraft and on the wings. Okay, so we will do accident investigation in the next lecture. That is day after tomorrow.